So they asked me to talk about what can you do with ROS-Industrial today, which has in large part been covered by previous presenters. It's also kind of a tricky topic because, as you've heard, ROS is used for all sorts of things all over the world, so trying to cover that in 30 minutes is kind of a challenge. So I'm going to narrow down the focus and talk explicitly about the parts of ROS that are applicable to an industrial setting, because that's why we're all here. And in particular also focus on the today aspect of what you can do. There are some cool things being done with ROS, but some of that requires, maybe man years of custom code development that sits on top of ROS. And so for me to stand up here and say, look at what you can do with ROS, and then you go home and try and expect to be able to do that with your systems without all that custom code, that would be kind of disingenuous. So what I'm focusing on are industrial things that you can actually do pretty much out of the box with what's in there. And there will be some overlap, but I'll try and breeze past that stuff. I'm going to start talking about, at the lowest level, with what kinds of hardware devices we can talk to, and then kind of bridge up to a summary of which pieces of the core ROS capabilities that have already been mentioned that I think are especially applicable in an industrial environment, and then at the end wrap up with, given those capabilities, what are some types of applications that would be good targets that are matched well against the strengths that ROS brings to the table. So talking about hardware, first and foremost, what kinds of robots can I use with ROS? Currently we have drivers for 5 different robot manufacturers: ABB, Fanuc, Motoman, Adept, and Universal Robots. For each of those robots, we have a couple of models that we've built the configurations for and done testing, and we know that they work. If you have a robot, that specific model, then it really is just download the software and start using it. If you have a different model robot from one of those manufacturers, there is a little bit of setup that you have to do, but it's all configuration based. There's no additional software that you have to write. So some of this, it can all be done in wizards. If you bring your robot into SolidWorks, then there's a SolidWorks wizard that you can run that will generate the URDF file that Sachin mentioned that essentially captures the geometry and the physical mesh of your robot. That lets all the visualization tools display those pretty graphics. And then once you export that from SolidWorks, you can bring that into the wizards inside of ROS to be able to spit out all the configuration files that ROS needs to be able to use your robot. You saw in Sachin's movie, the step that walked through the ROS wizard and the SolidWorks wizard is about the same level of effort. So I would say to bring in a new robot model from an existing manufacturer we already have drivers for is maybe a couple-hour process at the top side, and you just have to do that once and then you're set. So that's pretty straightforward if you have a robot by one of those manufacturers and you just need to add a new model. If you have a robot from a new manufacturer, say if you have a KUKA robot, we don't have any drivers for those yet, so you do have to write some software in that case. At a minimum, you've got to write a program that sits on the robot controller that's able to listen to a standard set of commands that we broadcast from the ROS world over a standard socket, and then your robot code listens to those messages and replies back with the appropriate responses and issues the right kind of motion commands. If you have no special requirements for your robots, then that's it. You just write that little couple hundred line driver that sits on your robot, and everything else is off the shelf. But it is possible to replace or tweak some of the ROS components to implement robot-specific functionality in case your robot needs to do something, or maybe you can't communicate over a socket messaging interface, you have to use a CAN bus or something like that. In that case, this robot driver side of things may look a little bit different, but as long as your ROS node presents the same interface to the rest of the ROS infrastructure, then that robot will still be fully compatible with the rest of the ROS ecosystem. So if you have a new kind of robot to bring on board, a new controller, then there's a little bit of software to write, but because we've already got 5 of these on board, 5 different manufacturers, and there's a lot of template code to sort of look at and say, okay, I need to do that same sort of thing for my robot. If you don't want to go through any of that, then you can use the existing simulation environment that you've already seen to download any of the robots and just play with them in a virtual environment. You can do a lot of testing and demonstration and even code development all in that virtual environment without committing anything to hardware. And so even if there's not a match for your particular robot platform, you can go play with the robots that we do support, just to get a feel for how this all works. Yes?
Just curious, simulating the existing robot. Have you ever tried looking at talking to a hexagon?
I'll leave that to the Willow guys, but I think so.
You know what I'm talking about? Do it platform?
Yeah, they don't have.
We haven't, but I think I've seen it somewhere. Somebody in there talked to me. So that's got a unique set of problems. Yeah. You need 6 axis, 6 strokes. And the travel and yeah. I remember someone in Germany working with it, but I haven't actually talked to them.
Certainly the format for defining what your robot looks like is generic enough to accept that kind of a robot model. The question is whether the out-of-the-box generic numeric kinematic solver is sufficient for that kind of a mechanism, or if you have to provide your own kinematic solver in addition to your own robot model. But if you did that, then it would certainly be compatible. Besides robots, then there's also strong support for perception sensors. We've heard a lot about 3D sensing and whatnot, and so ROS has a ton of drivers to support those kind of things. Anything from standard industrial cameras that connect via FireWire or Ethernet, SICK LiDAR rangefinders or laser rangefinders, stereo vision cameras, flash LiDAR. The Connect structured light sensor is a popular one with researchers because it's a 3D camera that only costs you $200. It's not necessarily ready for the factory floor. The couple we've tried to do that with tend to crash every couple of days, but it's a good way to get in there and start playing in the 3D world without a lot of investment. Support for a lot of other sensors beyond what's on here: force sensors, RFID sensors, environment sensors. I just didn't bother to list them all up in here.
We're using that Connect sensor in the industrial environments already, and it's been 6 months of production. And
there you go. So in some cases it can work. From an I/O perspective, we're a little bit more limited. The current setup in ROS pretty much only works with an EtherCAT I/O rack. You can get these from Wago or Beckhoff or whatever, and so you can get them with whatever flavor of Snap-on modules you want. But in order to be able to control that I/O from a ROS program, you mostly have to set up a standalone I/O rack and directly connect that to the ROS controlling PC. We don't talk to DeviceNet, Profibus, Modbus. We can't control I/O connected to the robot. All those things are technically possible. They're just not in there in what you can do with ROS today. There are some other EtherCAT type gripper devices. The fancy grippers you can get from Robotique are an example, and those are also supported. We have a connection to machine tools, which is kind of exciting. We just came out with this bridge to MT Connect. So MT Connect is a standard interface to machine tools that comes out of NIST, and if your machine tool that you bought supports MT Connect out of the box, then the ROS Bridge software will talk to that MT Connect software and pass messages between that interface and the ROS ecosystem, so your machine tools and your robots can talk to each other. If your machine tool is not brand new, in fact, I don't even know if you can buy a machine tool that comes with MT Connect support out of the box, then you can buy what they call an adapter, which is essentially a dedicated PC that talks to your CNC and then it knows how to talk to MT Connect. So there's ways to get even legacy machine tools to talk MT Connect. But through this bridge interface that's here, we do support talking to machine tools, so that should open up some good possibilities for being able to pick any kind of machine tool you want and any kind of robot you want and enabling those devices to talk to each other. What's missing is the title of this slide before you get too excited. As Sean said, we don't talk to any PLCs currently. We don't talk on many of the industrial networks or OPC, and as a result, we pretty much can't talk to any industrial HMIs because we don't talk the kind of interfaces that they hear. These are all capabilities that are on our roadmap or on our vision for what would be nice to add into ROS-Industrial, but some of the prioritization of what actually is important to chase after and which things do we need to target first and all of that are decisions that would come out of this consortium meeting based on what y'all's needs and desires are. Any questions about hardware support? I think that's the end of the... Yes?
So the limitation then for industrial support, since the bulk of our safety, a lot of the safety systems now use safety-rated PLC,
Yep.
it kind of precludes that.
Well, I mean, you can talk over like dual channel hardware interfaces or something like that, right? And get that communications across, but there is sort of a bottleneck in there.
So this is something that we want to hear from you on tomorrow when we do our road mapping. But it's not like there's some technical hurdle, it's really just a lack of development time.
So I wanted to bridge into moving away from the hardware into what is a more mid-level capability. And again, a lot of these have already been covered, so I'll flap through it. We've seen a lot about how ROS is capable of turning incoming 3D sensor data into things that the robot can make sense out of, to isolating objects of interest from the background and then identifying what exactly are those objects so that you can decide how you want to sort them or kit them or whatever else. It hadn't really been mentioned, but there's a lot of capabilities in there for mobile platforms about automatically building up a map of your environment and learning how to localize yourself within that map to help maintain a good state of where the robot is in its environment. A lot of that's been developed for the 2D environment, but there's similar kinds of capabilities for a 3D environment also. So that might be a robot that's trying to enter a new environment or a confined space. If it's got a 3D sensor on the end of it, it can scan its environment on the fly and build up this map to know, say for an obstacle avoidance perspective, what kinds of things it needs to avoid. We've also seen a lot about the planning capabilities of ROS. So being able to determine a safe plan from point A to point B. A lot of the, right, in a traditional robot controller, you mostly got to spell out every step along the way that you want it to go. In the ROS world, you mostly say, here's where I'm starting, here's where I want to go, figure out how to get from here to there given these different kinds of constraints. In the video over here, you saw the robot trying to fish a stick that was almost too big for the hole to go through. It had to kind of turn it and work it out the right way. All those complex plans are calculated just by giving it a start and an end position, and the robot figures out everything else in between.
Can we move couches up staircases?
That might require some development on your part. We talked already about collision planning, but the real point to emphasize here from an industrial perspective is how those collision and distance checks really are real time. This is the kind of thing that as your robot is running a pre-programmed path, it's not just something that it can do ahead of time, but while the robot is actually executing, the code's fast enough to be calculating those distances and to be able to send a signal to the robot to say stop or avoid that obstacle or do something else, either in a monitoring an existing motion or in a teleoperation kind of scenario. We did some testing with some reasonably large meshes of several 100,000 triangles, and the timing on how long it took to do one distance check was almost too small to measure, essentially. We've seen a lot of the visualization environment, which is a key strength for doing offline development. The fact that you can set up your robot in your environment and plan these paths and things offline. Some of the work that we saw Sachin doing, you'd actually interact with the robot to drag the start and the end position, but you can use the same visualization environment running actual control logic code in the back end. The robot's running the same program it would run in the real environment, but you're able to see how it would behave in the visualization environment. So being able to test all that stuff offline means that when it comes time to port it to the real physical system, that's a lot easier. You've already worked out a lot of the kinks, and it makes that process go smooth. It's been pretty impressive the number of times that we've taken something that we got working in simulation and fired up on the robot for the first time, and everybody kind of crosses their fingers and has their hand on the e-stop, and it manages to just work. And that's pretty impressive to see something that you've never put on a hardware system before, and you plug it in, and all of a sudden the robot's doing something pretty fancy and complicated. The limitation of the visualization environment is that if you've got live sensing that you're needing to feed as input to your process, then the visualization environment doesn't support that. It only shows you what's going on. But Sachin mentioned there is a physics-based simulation environment called Gazebo that handles all of that. It's smart enough to know if you try and grab something, are you going to knock it over? Is it going to slip through your grasp? It's got a full physics engine in there, but it can also simulate feedback to your sensors. So if you've got camera sensors or laser scanners, the simulation environment can actually generate simulated data for those sensors to help develop your application. It's not perfect, right? This is another, sometimes the computer virtual environment doesn't match the real world, but it gets you one step closer to being able to prototype things in software before you actually have to put them in hardware. And if all that doesn't work, there's also capabilities to record and play back data, which sounds like kind of a trivial thing, but it can enable faster development cycles without having to have hardware in the loop every single time. So in this case, we've got an autonomous vehicle that's running some ROS software to do perception processing and figure out exactly what it is in the environment that it's driving through. We don't want to drive that vehicle around every time we make a small software change to see did that work or not. So we drove it around campus, captured a bunch of video and laser scan data and saved that all off, and then spent months developing the algorithms just by playing that video back, running the algorithms and say, do they work? No. Okay, we tweak it and run the same video that we've already saved and keep running that same data against the video that we've captured, and being able to iterate that way is pretty valuable. And in that case, that's real sensor data you're playing with. It's just not interactive necessarily. So all of those we're talking about offline capabilities. You can use the same visualization tools for online processes also. So the same visualization environment can connect up to a real robot and update the virtual picture based on the actual robot position, which is okay enough. You know, you can make a movie, a remote screen showing what your robot's doing in the work cell, but you can also overlay data in that visualization environment to say not just physically what's moving, but what's being perceived, what is the robot thinking about its environment, what is it trying to do. So here we've got different zones, and you can tag things with how the robot has identified objects and what it's planning to do with them, where it's planning to move. Pretty much whatever you think of, you can add into this and create, I called it an augmented reality display. But there's some fancy things you can do with visualizing an online process there. And we talked some at the beginning about the hardware independence of ROS, but I think that really is a good capability from an industrial user perspective, because it frees you up. We've already talked about not having to port your software from one robot to the other, but it's also helpful if you've got a facility with robots from different manufacturers and different work cells, or maybe you've got two facilities that both do the same thing, but they do the same thing with different robots. In this case, you can have one software base that's used at both installations instead of having to maintain two different sets of software stacks. Just gives you a little bit more freedom, even if you're picking, trying to select a robot for a future work cell that's yet to be developed. If you plan to use ROS with that work cell, then it doesn't really matter as much from a software perspective which robot you choose. You can pick the robot more based on its physical capabilities, its payload, its kinematics, the design of that, maybe even what's more maintainable or easier to get, what you have on hand. So just the freedom to be able to be more independent from the specific robot type is I think, a good strength for particular clients. I also put together a what's missing slide from the capabilities. We've talked a lot about all these fancy things that ROS can do, but coming from an industrial controller background, there's a few things that you might expect to be present in ROS that aren't, just because there hadn't been a need for these yet. So the top on my list that I put here is precision control of position, velocity, and timing. You know, there's tools in ROS to really get in there and set constraints, but in some cases, they're kind of buried down in there. On a typical robot controller, it's right there. You say, here's my move command, and I want to move, you know, within this close of my termination point, or I want to maintain this velocity, or I want to move around a corner. There's all sorts of specific controls tailored to make sure that you can make the robot follow the exact path that your process needs. Some of those tools are within ROS, but it's more geared towards currently flexible path generation to deal with dynamic environments. And if your process needs a very specific path that follows very specific motion constraints, then there may be a little work to do with ROS to guarantee that what comes out of the end of the robot is really what you need for your process. Related to that is this bullet down here, motion-related triggers. So sometimes when you've got a process and you need to turn the paint gun on, you know, after you're at velocity, or turn something off right before you get to your target point or whatnot, those kinds of triggers aren't really available in the ROS ecosystem. You fire your motion trajectory and the robot starts executing that, and you can monitor that trajectory as it's going on, and when you see the right condition happen, you can fire the I/O, but there's some latency and some lag in that whole setup. So if your process has some real specific conditions that need to happen based on path timing, then that's a little difficult to do in the current setup. Many industrial robot controllers come with a simplified teach pendant interface. So if your maintenance guy needs to write a program, he picks up the teach pendant, and there's only like 3 things he can do with it. So he says, I need to do a move, and jogs the robot to where it needs to go. All ROS programs currently are either written in C++ or Python, which is great for developers, but it's not something you want your factory floor guy doing. So currently that's an area where it puts some things off the table that you may have been able to do. ROS doesn't replace any current functionality of your existing robot controllers. It just supplements them. So all of those core capabilities that were in the robot controller before, you can still write a teach pendant program and run it on the robot controller. It's just going to be run for that robot, not in the ROS ecosystem. So I'm not meaning to say that you can't do it, you just can't do it from within ROS. Dynamic path modification, I would say, is another limitation. So if you're trying to do something like seam tracking and you've got a sensor that's measuring where that seam is, and you need you're issuing a move command and you need your robot to kind of adjust its path on the fly, the current implementations, again, are mostly fire the trajectory and the robot executes it. And you can detect with a sensor and say, I'm off of my trajectory, but you don't have a whole lot of tools for being able to correct the trajectory that the robot is executing and fix some of those offsets. Again, these are, like I talked about on the hardware slide, these are all things that are technically possible. So I'm not meaning to say you can't do these in ROS, you just can't do them today. So again, these kinds of things, or whatever y'all would brainstorm, are the kinds of things that are on the table for potential future enhancements. I wanted to move on to applications, and these are my ideas for things that you would want to do in your factory that would be good fits for the capabilities we've talked about with ROS. A lot of these are pretty common sense, and maybe things y'all are already thinking or already doing even. So this example is if you've got an unknown part stream. So maybe your robot's sitting there and your particular work cell gets a constant stream of incoming parts and no 2 parts are the same. You've got a tremendous volume of different kinds of parts. Maybe every part is unique. Rather than trying to build a robot path from CAD data or teach the path for the robot for each part, it would be nice if it could just automatically generate it. And ROS is well suited for that. We've talked about the 3D sensing. You can scan the part. You can build up a knowledge of what that part looks like and then build your process path to do a raster scan or edge following or find key features for inspection. And all that stuff is generated on the fly for the robot to execute. So that would be a difficult problem to solve with a traditional robot controller, but the flexibility of the path planning and the sensing in ROS is well suited for unknown incoming parts. Similar to that is bin picking. So in this case, maybe you've got, yes?
In the previous slide you presented, a big challenge is the grasping.
It depends on what your process is, right? So some parts that require grasping, Sachin already showed that there are automated grasp test modules inside of ROS that will test different possibility of grasps to find the one that will grab the part. But maybe your process is a grinding or a painting or something that doesn't require any contact at all, in which case grasp is less of a problem.
So there is some support for grasp planning.
Yes.
There is support for grasp. You can do it both offline and then configure. Yeah, and you can do it online.
Bin picking, so in this case you use a lot of the same technologies. Scan your bin of parts and try and identify which parts are discrete and generate the automatic paths for the robot to pick it up. The challenges here are identifying what is the right order to pick your parts. You want to pick the things that are on top first, and maybe identifying where is the right spot on your part to grab and grasp that particular part. Some of those features are application specific, so those are not necessarily core ROS tools. It gives you a lot of perception tools that you can use to build your custom application out of, but out of the box you may still have to write some custom stuff to get bin picking to work, but I think the right tools are in ROS to enable that. Mobile robotics are a hot area, and initially when I put this slide up I thought, well, maybe not many people are thinking of of ROS as being something that's good for mobile robotics, but I think everybody's already talked to that. The PR2 robot, that's kind of the flagship initial ROS robot, it's out at universities all over the place. That's what they're using for their research. That's essentially a mobile robot. It's got a base that can drive around and an arm that can interact with the environment. So even though that particular robot configuration is not one that you would necessarily deploy at your factory, the tools that are developed for that to navigate the base around, figure out where to position it, and how to move the arm to interact with the environment, those same tools are tools that you would want to use for a more industrial mobile robotic application. And as Paul mentioned earlier, traditionally you might have one controller that's the arm controller and one controller that's the base controller, and trying to get those things to talk to each other or have a high-level planner that would direct those separate controllers for what to do is kind of messy. ROS is almost built from the ground up, given that the PR2 is kind of its flagship, to be ready to support both of those things from one control environment. So it's nice to have that as a fully integrated system instead of trying to treat the base and the arm as two discretely separate things that you somehow manage to smush together. A couple other ideas that I just threw up here are dynamic environments. So if you've got people or obstacles moving in and out of your environment, you want your robot to be able to detect those obstacles and avoid them or just wait for them to get out of the way. We've already seen how that works. Low downtime, so if you've got a high availability cell that really can't afford being down for long to spin up your new application, then the fact that there's these strong offline development tools means that you can get so much more work done before you need to push that system out to the hardware, that if you've got a system that really can't handle very much downtime, then being able to do all that development in an offline sense could be a key strength. And then the last application that I put down was a heterogeneous workspace. So if you've got different work cells with different robots, then the hardware independence of ROS might be something for you. And then I couldn't resist, so I had to put up one last slide of less industrial applications. So if you go out there and you look on YouTube for what can ROS do today, you see all sorts of grad students with too much time on their hands. But my takeaway is if a robot can fold laundry or get a beer from the fridge, then there's a whole slew of industrial type manipulation tasks that it should be able to handle somehow. So in summary, from a hardware support, I think we've got fair coverage for robots and a pretty good map for how to integrate new robots. We've got a lot of visualization sensors that are supported, and we're kind of weak on the I/O standpoint currently. There's strong capabilities in the areas of 3D perception and planning, which means for applications having dynamic environments with different kinds of parts moving through that you have to create those plans on the fly rather than teaching one path ahead of time that the robot's going to do. I think those dynamic environments are the kinds of things that are best targets for ROS today. If you've got a simple pick and place where you're doing the same motion, hundreds of thousands of times, then ROS is maybe not the right control system for that. But it still might be if the value of standardizing the control interface and the monitoring interface, maybe just that standardization in a robot-independent way is value added enough on its own. Here's my giant picture too. Mm-hmm. Yeah, what kind of robotics engineer? Yeah.
From a system integrator and a factory user, granted it's not quite there yet for that use, but what would be the job description of a person who would use that?
Mm-hmm.
It would also help you define what you need to do to get to that point.
Right. I mean, clearly we want to push towards making it easier to use for as many people as we can, but it would be nice to sort of benchmark where we are today to get a handle of what that is.
The disconnect in between the people, a lot of people sitting in this room and what you see and when you walk into the other world
Mm-hmm.
is so significant that they don't even know where to begin, where to hire a person, and what kind of qualification you should have. And so helping them with that would take one thing off their checklist.
Yeah, that's a good thought. Yes.
I know Sean talked about this briefly in the conference call, but I'm still not quite sure about my brain around it. You have drivers for the 5 robotic industrial manipulators. How much is it simply hooking into their controller and using a low-man API type thing? How much of it is hooking in and mimicking what their existing be in the teach pen, it would be in maybe some sort of run mode, it would switch to a teach pen mode, so the teach pen still technically exists for the on-site supervisors who
Mhm.
react to a certain situation. Can you comment on how you get those developed and added?
Yeah,
How
so
they differ from robot to robot?
So right now we have erred on the side of simplicity for the robot drivers. Essentially, the only commands that we send to the robot are lists of joint positions that the robot needs to follow, and primarily the feedback we ask is position and velocity and some status information. So it's kind of a minimal set of what you need to do to get the robot to function. And we've defined a standard socket message to get that data to and from the robot. So at a minimum, if your robot lets you write raw sockets, which is a programming interface, and you can translate those sockets into motion commands for the robot and read the current position of the robot and translate that into socket messages to go out, that's the minimum of what you need. So from that perspective, a lot of the robot controllers have very similar looking interfaces. If your robot doesn't want to support that socket library and wants to use a proprietary API or a CAN bus or something else, then you jump up to the next level. So let me see if I can get my little picture back here. So that's the level down here. This communication here is often that standard socket interface that we have defined. But we also have a standard interface defined here that's the same as ROS uses to talk to the PR2 and other robots that says these are the types of ROS messages your robot needs to respond to handle joint motion and provide the right kind of feedback and whatever. So some of the robots in our little map, for example, the universal robot over here, doesn't use our socket messaging interface to talk to the UR5. It just uses something else, but as long as it provides that standard interface to the ROS level, then it's still fully compatible with all the upstream tools. We're trying to convince as many people as possible to implement this interface, because then whatever we do at this level is common to all those robots. But if that doesn't work and all you have to do is adhere to this interface, then it's just more work to keep everybody in sync when we want to try and add new features to this middle layer. Does that answer your question?
It does. Of those 5, how many, so you've got 4 out of 5 that have developed and actively developed the socket interface, and 1 that's kind of passively allowed you created drivers around the side?
I think that's correct. I think all 4 of these utilize that socket interface, and then this last one over here jumps to the next level higher and talks at the ROS interface.